Hi guys, in this video we're going to talk about solving right triangles that involve angle of elevation and angle of depression. We're going to just do 3 examples, and in the first example I will explain what angle of elevation and depression is. A forest ranger is on a fire lookout tower in a national forest. His observation position is 215 feet above the ground when he spots an illegal campfire. The angle of depression of the line of sight to the campfire is 3 degrees. How far is it from the base of the tower to the campfire? Okay, let's take a look at what's going on here. So the angle of depression and angle of elevation are here, and the tower is 215 feet above the ground, and then we're looking for this distance. So let's talk about the angle of elevation and depression for just a second. So if you recognize these angles, you should notice that they're essentially alternate interior angles. So we have alternate interior angles here. Now what happens is we can see symmetry in things that are looking down at us that we're looking up at. In other words, when I am standing on, let's say, a ladder, and then looking at something on the floor, or looking at another person, that person is turning their head in the exact opposite angle of me, creating these alternate interior angles. This is real-world trig application here. For example, in cars we use pinion angles, which does much the same thing. In airplanes, they use these angles to figure out their descent and incline. It's pretty common. But in the end, all they are is alternate interior angles, and it does not matter if I have the angle of depression or angle of elevation to solve for a right triangle. I would like to discuss one quick thing before I solve this problem, and one of them is the physicality of this math. So, trigonometry is probably one of my favorite things to teach, next to the quadratic formula. And the reason for it is because you can physically apply the math and see what's going on. In this case, what we can do is we can consider these angles in these triangles. So I quickly tried to just draw these triangles to scale. This is a 45, 90 triangle. Let's say that that's what that is for argument's sake, which is also an isosceles triangle. This is our 3-degree triangle. I'm probably being slightly generous in that angle, but just to show the discrepancy of, or what that angle would look like to scale that triangle, and then the discrepancy between the sides. So when we have an isosceles triangle 45, these sides are the same. The farther away we will get from 45, the more change we will see between the 2 legs. So what am I trying to say? Okay, in this particular case, when I do the trigonometry, I can have an expectation for my answer. I know that when I solve this problem, I am going to have a leg that is significantly larger than 215, and I could place that in consideration. So now, let's solve the problem. Just like in the previous trigonometry videos, I am going to go through the steps of labeling the sides of the triangle. So this is the opposite side, this is the adjacent side, and that's the hypotenuse. You can essentially ignore this part of the rectangle if you like. It doesn't matter. If you are familiar with the proofs videos that we have done, or familiar with geometric proofs in general, you would know that those 2 triangles are congruent. From there, I have the opposite, and I'm looking for the adjacent leg. So that's going to be tangent. If you need a review, you could check out the previous proof video that I posted, or you can just go watch the millions of trig videos that are probably all over the YouTube, and they will almost all say the same thing. So now I am filling in my proportion, and I am cross multiplying. So this is 215 equals x times tangent 3. Then I'm going to divide tangent 3 to both sides. And we're going to see what my calculator says. And my calculator says 4,102.44 feet. Which is part of the reason why I spoke to the consideration of what these triangles would look like at scale, so this way you're not shocked at this answer. Most angle of depression and elevation problems will involve tangent, and part of the reason is, once again, for me to stress this, these problems are happening in a physical world. So the only way to really avoid tangent in these problems is if you can fly, or you're in an airplane. So the pilot of a plane is flying at an altitude of 18 kilometers and is getting ready to land. He spots the airport at an angle of depression of 10 degrees. Find the actual flying distance to the airport. So if I remember correctly, which I may not, I believe this is called the angle of attack for airplanes. And they have a gauge on their, let's say, cockpit or dashboard, if you're not that familiar, that gives them this angle. And it is called a horizon indicator. So now we're 18 kilometers up. Let's see if I could actually draw an airplane. There we go. And here's the runway. Now, I obviously never recommend you do this, but just for the sake. And what I want you to understand is that the point at which the pilot is looking down at the runway is looking back at the airplane, creating that alternate interior angle. So if I were to draw it, which I also don't recommend, that angle is here, and that's 10 degrees. Okay, so this plane is going to nosedive into this airport, and we're going to take a look and see how far it has to fly to actually create that nosedive. And I'm going to do that by using the same procedure or algorithm as I have before. So this is O, this is H, and that is A. And in this case, we're going to use sine, because I have the opposite leg, and I'm looking for the hypotenuse. So sine of 10 over 1 equals 18 over x. Now these are kilometers. I'm going to cross multiply and solve. I've mentioned this before. As comfortable as you get with trig, I would not really skip this step. It's one of those steps that you skip, and it's very easy to create an error. And now I'm going to plug that into the calculator. 18 divided by sine 10 gives me 103.65 kilometers. That means that pilot needs to travel 103.65 kilometers at 10 degrees to land at the airport. Okay, let's take a look at some fire trucks. So Coughlin is on the 4th floor of a burning building. The stairs are blocked and the elevator is not working. He finds a window which he estimates is 40 feet above the ground. He sees a fire truck through the window at an angle of depression of 42 degrees. If the base of the ladder is on top of the fire truck, which is 8 feet tall, how long of a ladder is needed to rescue Carlton? Okay, let's talk some business here. For starters, we do not apply trig this way. on a daily basis. So in other words, I would find it hard to believe that a firefighter is going to pull out his calculator, or her calculator for that matter, and say, oh, let me start doing some trig to figure out how tall I could reach or what ladder I need. Okay, the ladder is attached to the fire truck and the ladder extends to its position. But somebody has done this trig in designing the fire truck. So in other words, the fire department is probably notified exactly how tall they can reach with a specific fire truck and how far the ladder extends and where that will get them. So somebody at some point is doing the trig, but it is not in this scenario. Alright, this is a standardized test question, so let's solve the problem. Okay, so I'm going to place the angle of depression here. It does not, because they're alternate interior angles, I always place the angle of depression at the bottom of the triangle. I never try to create that rectangle situation. And what I'm going to do is I'm going to label my triangles. So this is O, this is H, and this is X. Excuse me. A. We want to know what the length of the ladder is, so this is X. Okay, but there is a problem with this question. And the problem is this. You do not want this length. We want this length here. And that length is 32 feet. The reason why that length is 32 feet is because the truck itself is 8 feet off the ground, changing the dimensions of the triangle. So the way I got 32 feet is I subtracted the 40 feet of the building from the 8 feet tall of the fire truck to get 32 feet. Now I can perform some trigonometry. This is once again a sign question, and the reason for it is because we want to know the length of the ladder. Now let's get started. So I am going to write out my ratio. I'm going to plug in to that ratio, and I'm going to follow the same steps that I have before. In my opinion, as I go through this, learning steps to math is daunting in itself. But what happens here is the true challenge is how do we apply these steps to get what we need. My opinion is that is the true difficult thing to do, and it takes a long time. Trigonometry gives us a gateway to that because the steps are always the same. So we could consider, when we solve these problems, how do I fit the trigonometric ratio and the steps to use it into the problem that's being presented to me. So when I plug 32 divided by sine 42 into the calculator, I get 47.82 feet. The way this problem is written, the firefighter would have had to have done this trig prior to getting to Carlton and rescuing him, or else the firefighter would not have the appropriate ladder to rescue Carlton, which puts Carlton in trouble. That's a problematic problem to have. Alright guys, here's how we use the angle of elevation and depression to solve right triangles. I gave you two real-world scenarios and one that's a little sketchy. Alright, I hope you guys found this video helpful.